electric field and its intensity. The basic concept of electric field was introduced by scientist Faraday. Whenever there is a charge, it can influence the charges placed in its surrounding. The region in which it could influence the other charges is known as electric field. The intensity of this field is given by a particular formula, that is the force experienced by a unit charge placed at that very point. See, this is the formula, force upon charge. The unit would be Newton per Coulomb. In later studies, we'll find its unit to be volt per meter also. Now, if we calculate the force by a charge over the other charge placed at distance, say small r from it, we'll find the value we'll put here in the formula, and finally you'll get the relation for electric field at a distance small r from point charge equal to this much. See, in this relation, you must have noticed E is directly proportional to 1 upon r square. This is also known as inverse square law, which is common to gravitational field and at the same time magnetic field as well. One very important thing to be remembered is that when there is a positive charge, the electric field because of it is always away from it. And that due to negative charge, electric field shall be towards it always. In this formula, the important thing to be noticed is that this depends on the coordinate of the point that you have chosen for electric field. You might say electric field exists in 3D. What does it mean? It means that it is a vector and it might be having direction throughout the space. When you want to show uniform electric field, for that you'll have to follow this method, equidistant parallel line. But you see, the production of uniform electric field is a bit typical and one of the rarest phenomenon, because here you have just noticed that electric field will be affected by the distance. You might say it is distance dependent. Electric field lines can never intersect each other like this, because at the point of interaction, it will give the inference that electric field is along two directions, where it is just impossible. A vector is always along one particular direction. A vector, when I say one vector, that means the resultant vector shall be always along one direction. If there are many charges, many charges, and you want to find the resultant field at a particular point, then what you have to do is simply find the electric field by all the charges and try the principle of superposition. Or you might say simply in mathematics, you have to find the vector resultant of all the electric field. Then we have covered all the points. One point you have to remember, if say this is a triangle, I will first explain with the help of a triangle, then we'll generalize it for a polygon also. Suppose it is a equilateral triangle and similar charges. It might be plus q, it might be minus q, but all the charges are similar and have been placed at the three vertices of a triangle that is equilateral. The field at the center of mass of the figure shall be equal to 0. Now, you could say in general that if equal charges are placed at the vertices of any regular polygon, then the resultant field at the center of mass of that very figure is going to be 0. One more important result you should remember by heart. Suppose there are two charges, similar charges, and you choose any point on its perpendicular bisector, I mean the perpendicular bisector of the line joining the two similar charges. Here, if you consider the field because of one charge is going to be away from it, similarly that from others going to be away from it, then the resultant shall be across the line itself. The resultant field throughout this line on the perpendicular bisector is going to be along the line itself. If the two charges are positive, field would be away from it. If they are negative, field would be towards the center of this line of joining the two charges. Then comes one very interesting case that needs a little carefulness for understanding. You see, I would consider here two charges. Both the charges are similar. And suppose this line is considered. This is the middle point of this line. We want to find the electric field at different points of this line. But for that, basically at first sight, you might say that the resultant field at this point is going to be equal to 0. That's not point of concern. Point of concern is throughout this line, what shall be the value of electric field at all the points of this line? Obviously, if you consider this very point itself, the field is going to be infinity. And here as well, the field is going to be infinity. But what happens in between? Here it is 0, at the two extreme it is infinity. But what about other points? To show that, we would take electric field along this axis. Means to depict this, we are assuming that electric field would be plotted along y-axis. Its magnitude, its value will be shown along y-axis. And just a line, you see. Here, I told you the field would be 0. This side, it's almost touching. You just don't touch the graph with the axis because that gives the value infinity, which is not presentable here. So, line goes a little away from it, this way. What we are trying to convey here is that both the sides, the field, if you consider here, it is infinity, no doubt, but just before this, the field would be this way. Why? Because the charges are positive. So, because of this, field is less, but this is very high value because of this charge, and field is almost infinity over here. This side, resultant field. If you consider the point here, field would be this side. So, that's why we have tried to show the field at either points in opposite direction. And what remains here is, when you give the charge to any metallic conductor, you see the shape, the size is geometry of that conductor is not material. The result that I am going to describe here is independent of the shape. If you give the charge will be confined to the surface only. Means the charge that you transfer, it's going to be confined on the surface. Inside there won't be any charge given from outside. So, the resultant field inside will be always equal to 0. And if the electric lines are approaching this conductor, they will meet the surface of the conductor always normally. Better you could say the angle between the lines and the surface is always going to be 90 degrees.